Here is P-plane. When you start P-plane, this is what it will look like. You will have these windows. This is the phase plane. This is P-plane messages. And you will get this informational screen, which you don't need, so you can almost always get rid of it right away. And then it will give you this default model that you can see in the lower left-hand side. That's the default model, which of course you'll change to use to simulate whatever model we're working on. So let's go ahead and do the first example from today. So x dot equals minus y, and then y dot equals x squared minus y plus u. And it doesn't like this red because I didn't give it u yet. Now it's happy because I give it u. And let's go ahead and use 4s all around for the size of this window. And let's graph the phase plane. So I'm pressing graph the phase plane. If you don't like the look of this, you can do options, background, black, and then it'll change it. And now we want to see null clines. So we'll go to Solution, Show Null Clines. Boom, there's your null clines. So far, so good. Now, I'm going to want to show you some solutions. If I put my cursor down, boom, it goes both directions, goes backwards time, forwards time. I don't like that. So I'm going to stop that, and I'm going to recalculate all the orbits. I'm going to show the null clines. I want to get rid of this. I want to get rid of this trajectory. Okay. There's a way to blank the screen, but I'm forgetting how to do it. Okay, so I'll go back to my system. And yes, delete all orbits. Thank you. You know, it's much more nerve-wracking when you're doing it in front of a class. Like if I were at home, I would have figured that out like that. You don't. Thank you for that. Okay, so show the null clines again. Now, I don't want to see it go backwards in time. So I'm going to go to Options, Solution Direction. Instead of both, I just choose forward. Now when I put a trajectory down, it only gives me the forward in time. So now you can see I can begin to figure out that this is a saddle point, and the one on the right-hand side is an equilibrium point that is a stable spiral. So now, what should we do next? Do you want to see the stability of the equilibrium points, or you want to see the stable and unstable manifolds of the saddles? Saddles? All right. So let's do what we did before. Let's delete all the orbits. And we know that the point on the left is the saddle. So then I'll say solution, plot stable and unstable orbits. And then I'll click now on my point, and boom, now I have them. Now, just by looking at the flow of those arrows, you can see which one is the stable and which one is the unstable. The darker tealish line, that's the stable manifold, and then this one is the cyan line is the unstable manifold. And the unstable manifold makes a heteroclinic orbit with that equilibrium point. So now you're probably saying, okay, I want to see how do I figure out the stability of the equilibrium points. I know the keyboard shortcut is Command-E on a Macintosh, but if you don't know that, you can go to Solution, Find Equilibrium Point. And now I have this click on a point near equilibrium point. And so I go near my saddle, click it, and boom. Then you look in your P-plane messages. There is a saddle point. That's my Jacobian. There's my eigenvalues, one positive, one negative. How great is that? Okay, so let's do the other one. So then I'll go back to my P-plane window, Solution, find an equilibrium point, and now click near this which we think is a stable spiral. Boom, click on it. There is a spiral sink, or stable spiral, at this point. There's your Jacobian. There's your eigenvalues. And look how it, presents those eigenvalues. Negative 0.5 plus 1.6i. Negative 0.5 minus 1.6i. You see that? Mu, the real part of the eigenvalue, is negative in both cases because the damn thing is stable. But you have a plus imaginary and a minus imaginary for the rotation. So it computes all of it for you. All that symbolic mathematics and linear algebra that we did in 13.2, this software will do it for you. And as you get more sophisticated in your nonlinear dynamics and you start building neuron models for research, you can just get more sophisticated software because already, one of my students tried to put the Morse-Car model into P-plane and it doesn't work. It's too complicated. P-plane can only work with more simple polynomial models. If your equations get too complex, it will complain. But as long as you're dealing with polynomials, it will do all this for you. Want to do another example? Do you like the dark mode or the light mode? Yes, sir.
Can you explain what the teal line is?
The teal line it's bluish teal, and I know it's stable because the arrows are pointing it towards the center of the saddle point. Does that help? That's why, sir, in the beginning, you want to go here to Options, Solution Direction Forward, so that you know when you drop a point down, it's only going to show you forward time trajectory. So now if I go right here, you watching? So, well, watch my cursor. If I drop a point, boom, you can see it. It headed into the stable manifold, and then it veered away at the end. So if I put a point right here, drop it, boom, it just goes away. It launches away. But if I put it like right here in this upper corner, watch it head in and then go away. Got it? All right. So shall I do another example? All right. So I'll go back here and let's see. I'm going to go to this example, which was example 4. X dot equals minus x plus x cubed. X times x times x minus y. And then the y equation was minus 2 times y. And I don't think I had a u, so I can get rid of that. Graph the phase plane. All right. This one, the cubic is kind of small, so I actually want to maybe zoom in on the plane here and get a little bit closer. So maybe I'll make everything between minus 1, 1, and 2 on the x-axis. So I'll go down here, minus 2, maximum x 2, minimum y minus 1, maximum y 1. Now it's a little bit bigger. All right, you're looking at this and you're saying to yourself, I think I understand what all these points are, but let's do some trajectories. So options, direction forward, put it down. Okay. What do you think this is? Stable node. And then go over here. What do you think this is? Saddles. So it looks like we can understand the system pretty easily. So okay, let's do it. So now I do solution, find equilibrium point, click on my point, boom. There's a saddle point at negative 1, 0. There's your Jacobian, there's your eigenvalues. Eigenvalues, one's positive, one's negative. Lambda 1 is positive, lambda 2 is negative. All right, I'm not going to bother to do it on this side because it's going to be it's going to be quite similar. So I'll do the one in the middle. Solution, find an equilibrium point, go into the center, hit it. It's unhappy with that choice. There we go. I clicked too far away from it, and the Hartman-Grobman theorem said, you're a little bit too far away from the equilibrium point. Remember, the Hartman-Grobman theorem only works when you're really, really close. And I clicked too far away from it, it complained. So now it said, there is a nodal sink at point 0, 0, the origin, and there's your eigenvalues and eigenvectors. Negative 1, negative 2. 2 decaying modes. No imaginary, because it's a node. How are we doing? All right. Want to do another example? We have enough time. Want to do the one with the center? I do too. So I think that was example 5. If it's not, I'll quickly move to the different example. So this should be y minus y cubed. And the second equation is minus x minus y squared. Yep, there it is. So there's our phase plane. Notice I did not call it a phase diagram, I called it the phase plane, giving us our null lines, giving us our flow field. So let's do some trajectories. So there's our first neutrally stable orbit. Probably that's a center point. Now we start to see the saddles. So let's check our equilibrium points. Solution, find equilibrium point. Let's go for the origin. Boom. Now, notice, it's a little unhappy. There is a spiral point at 0, 0. Its specific type has not been determined. So occasionally, the software will not be able to give you a definitive answer. It's going to get confused. So what happens? If it says there's a spiral point there, at least the software is acknowledging that it recognizes imaginary eigenvalues. But it can't figure out whether it's stable or unstable. So then you just have to use your intuition. You jump in and say, look, I plotted a bunch of these trajectories, and I can clearly compute the trace and the determinant. The trace is 0 plus 0. It's 0. So you know there's no growing or decaying modes. So even though the software failed you, it tells you the Jacobian correctly, and you can compute the trace from that. Now, in exam 3, exam 4, and the final exam, I will have the characteristic equation, the quadratic equation, all these things that we've been looking at today, all those equations will be on the last page of the exam, so that if you're like, oh yeah, P-plane is telling me the Jacobian, but I can't remember what terms I put together to get the trace. Well, just go to the back page. If you know what you're looking for, when you see it, you'll recognize it. And look, even though it didn't determine it, it got the eigenvalues right. 0 plus I, 0 minus I. So even though it got confused, it tells you the right answer. It is 3:18. What else could I do that I haven't done yet? Let's look at the menus. We did plot stable and unstable orbits. Show null lines and arrows. It does that automatically. Graph. Yes. We can ask for trajectories versus time. I'm not going to do that today because these don't really look like action potentials. But in our next lecture, we're going to do what's called the Fitzhugh-Nagumo model of the action potential, which can be run in P-plane, and we will use it to show you repetitive action potentials. So this will give you time. This will give you time series. Berkeley-Madonna's default is to show you a time series. And then you have to ask Berkeley-Madonna to show you a phase plane. P-plane, its default is to show you the phase plane, and you can ask it for a time series. Options. You can change the font size, show the crosshairs. There's lots of different things you can do. But it's 3:19, and I think I've covered just about everything. You can change your Runcutta Dorman price if you want to. I think I've done just about everything for today. See you Thursday. Hold on a second. Hold on a second. Yeah. I see it didn't come through. That's why it didn't come through, huh?
Yeah.
Okay, that's why people were photographing it.
Yeah.
I gotta figure out how to stop this damn thing. I can't figure out how to stop this.
Wait a minute. When are you gonna be around today?
Can I just let me just stop this thing? I'm trying to figure out how to stop this video so it doesn't go on and on and on, and I can't figure it out. Damn it! How do I stop this damn thing? Just give me a sec, all right? Yeah, I know why you're here. do.